Hey everybody! Check out the newest addition to my lab. This is a scanning electron microscope. When this machine was new, it would have cost over $100,000. This particular machine was broken, so I got it for free. After months of effort, I managed to get it working again. This video is the story of how that happened. Let me start from the beginning. Microscopy is one of my oldest hobbies. I got my first toy microscope in grade school, and in high school I saved up my money and bought a much nicer one. You might even recognize it, as it's been used multiple times on this channel. Fast forward to college, and I managed to snag an internship at a lab researching nanostructures. These structures were so small that even an optical microscope was not enough to see them. And so I received training on the lab's Scanning Electron Microscope, or SEM for short. I was immediately blown away by the images produced by the Scanning Electron Microscope. Features that were far too small to see under an optical microscope were visible in extreme detail in the electron microscope. But how was this possible? Well, it all comes down to wavelength. You see, the wavelength of light imposes a limit on the maximum resolution of a microscope. Visible light has a wavelength between 400 and 800 nanometers, around the size of a bacterium, and so optical microscopes really can't see anything smaller than that. Electron microscopes, as the name suggests, use electrons instead to create an image. The wavelength of these electrons can vary, but are typically around 100 picometers. This is more than 1,000 times smaller than the wavelength of visible light, well into the X-ray range. It cannot be overstated how much of an improvement this is over an optical microscope. Optical microscopes typically max out at around 1,000 times magnification, whereas some modern electron microscopes can exceed 1,000,000 times magnification, allowing us to see even individual atoms themselves. The first day I used the microscope, I decided right then and there that one of my life goals would be to own one of these beautiful machines myself. There was just one problem. Unlike optical microscopes, which are small and relatively inexpensive, electron microscopes are behemoths, usually weighing in at thousands of pounds and occupying an entire room on their own. They are also extremely expensive, usually hundreds of thousands of dollars. Buying new was out of the question. However, I realized that as technology improves, labs replace their equipment, and so occasionally, old electron microscopes go up for sale. Thus began my decade-long search for a used but functional SEM. I found a few potential candidates over the years, but they were all either too expensive or entirely broken. However, about a year ago, I stumbled upon a small scanning electron microscope on Craigslist of all places. It was made by a company called JEOL in the 80s and 90s. It was relatively small for an SEM at least. Only about 800 pounds and the size of a single desk. However, when I inspected it in person, I found that it was totally non-functional. The lab selling it told me that they tried to repair it themselves, but got nowhere. So they promptly stuck it in a warehouse and forgot about it for 10 years. I declined to buy it, but I told them if they ever wanted to scrap it, I would gladly take it off their hands for free. 6 months later, and to my complete surprise, I got a call back from the same lab. Apparently, no one else had been interested, so I got a friend and a truck and went to pick it up, along with a box of manuals and schematics. It was then that I realized I was in over my head. I only knew the very basics of how a machine like this worked, and certainly not enough to repair one. To remedy that, I devoured information from books and online, quickly learning how these machines were built and how they worked. During that process, I managed to find this Discord channel of hobbyist SEM owners, and even found a couple of people, Martin and Monochroma, who were also fixing up their very own JSM 5200s. What incredible luck! I shared my manuals and schematics with them, and from then on, when something was not behaving correctly on one machine, we could leverage the other machines as a reference and more easily understand what needed to be fixed. So, how does a scanning electron microscope work anyway? Well, to start, a scanning electron microscope does not image the whole sample at once. Instead, it builds the image pixel by pixel. Here's how. We start by creating a very narrow beam of electrons. This beam strikes a very small spot on the surface of an object to be inspected. This causes the surface to emit electrons itself. A detector counts the number of emitted electrons, and that number determines the brightness of a single pixel on the screen. Then, the microscope moves the beam to the next spot to create the next pixel, then the next, and so on until the beam has covered the entire area to be inspected. You can see on the display that we have a very rough image of our sample. To fix this, we can make the electron beam more narrow, which will make the pixels smaller and result in a higher resolution image. In order to increase magnification, however, all we have to do is simply scan a smaller area. Pretty cool, huh? Okay, let's talk hardware. The microscope itself consists of several components, the most important of which is the column. This is where the magic happens. Electrons are generated at the top of the column here, and are fed downward through a series of lenses and apertures, which creates a narrow beam. The beam passes through a set of deflection coils, which allows the microscope to precisely control where the beam lands on the sample. The beam strikes the surface of the sample, causing it to emit electrons, which are then captured by this detector and counted. The signal from the detector is then displayed on this viewing screen as our image. Now, everything I just described is essentially the heart of the microscope. However, there are many other necessary components that this microscope needs to function. First, there is a vacuum system. Electron beams can't travel through air, and so the entire column needs to be held under a vacuum. And not just any vacuum. We need around 1/100000th of an atmosphere. To accomplish this, we must use 2 pumps. This is called a diffusion pump. Diffusion pumps are pretty crazy. They have no moving parts and operate entirely by boiling a special type of oil. Diffusion pumps can reach incredibly low pressures. However, they cannot exhaust directly to atmosphere. They can only exhaust into another vacuum pump. Thus, we need a second vacuum pump, just a normal mechanical pump, for that purpose. Diffusion pumps also generate a lot of heat, so they require water cooling as well. Next, we have a bunch of different power supplies, including one that goes up to 25,000 volts. This is the accelerating voltage that creates the electron beam. After that, we have a bunch of sensitive analog circuitry. This is a bunch of amplifiers and stuff that carefully control the current to the electromagnetic lenses that deflect and focus the electron beam. They are also responsible for magnifying the minute electrical signals that are produced by the detector. In addition to that, we also have digital circuitry, in the form of a rudimentary computer that manages the valves and other components and keeps the SCM operating smoothly. Finally, we have the user interface, made up of the main display which shows us the image, and a small LCD which shows us the system status, as well as a bunch of knobs and buttons which allow us to control the focus and magnification of the microscope. And that's basically everything. Okay, so we finally have the microscope, the documentation, and a rudimentary understanding of how this machine is supposed to work. But how do we actually repair this thing? Well, given that it won't currently turn on, it makes sense to check out the power supplies first. This machine runs on 100 volts AC, which is provided by this variac here, which plugs into a standard 120 volt wall outlet. I first checked the variac and confirmed it was outputting 100 volts AC before connecting it to the machine. While I'm back here, I'm also going to unplug the diffusion pump heater. The diffusion pump requires a constant source of cooling water and vacuum and isn't necessary for the upcoming tests. Okay, the machine's power is connected. Here we go. Okay, that was anticlimactic. It looks like the machine doesn't have power for some reason. Let's start by checking the power entry area. It looks like the 100 volts comes in here, goes through a couple of fuses, and a couple of transformers, which feeds a bunch of different power supplies. Well, right off the bat, I found a blown fuse. I replaced the fuse, turned the machine back on, and immediately blew the fuse again. Okay, I probably should have seen that one coming. Something downstream is clearly drawing too much current or is shorted out entirely. According to the schematics, this fuse protects transformer T2, which is this monstrosity here. It's a large transformer with 1 primary and 7 secondary windings. I checked each winding with an ohm meter and found that one of the windings is clearly shorted. What probably happened is that over the last 30 years or so, the old insulation on the windings deteriorated and shorted out the transformer. Because of the way it's constructed, the only way to repair the transformer would be to unwind, then rewind all 8 coils by hand. Realistically, this transformer is scrap. Now, sourcing a brand new replacement for a bespoke transformer like this is unrealistic. Fortunately, we have some alternatives. Instead of one transformer with 1 primary and 7 secondary coils, we can instead replace each secondary with its own transformer. And that's exactly what I did. Actually, it turns out that some of the secondaries were for optional hardware that this microscope doesn't have, so this was all I needed. There was one hiccup though. Remember that this is a 100 volt machine and most transformers are rated for 120 volts. This complicates the process of sourcing replacements, because a 120 to 12 volt transformer becomes a 100 to 10 volt transformer instead. I had to account for that. For my 60 volt power supply, for example, I used this large 72 volt toroidal transformer. For my 12 volt power supply, I used a 12 volt transformer. This only outputs 10 volts, but that's acceptable because it feeds into a linear voltage regulator that's tolerant to a lower input voltage. I mounted the transformers to an aluminum plate and found a place for them in the cabinet next to T2. I checked each output to make sure it was correct, and then wired it in. Let's see if we can turn the machine on now. Okay, that's not right. What in the world is going on here? Well, as far as I can tell, all of the digital logic is going completely haywire. That is not a good sign. I checked the schematics and found that the digital logic is fed by 2 different 5 volt power supplies. These power supplies are these ancient 5 volt linear regulators with massive heat sinks. I tested them and found their output voltage was wildly erratic, so they need to be replaced. Now, this part is so old that I couldn't get any relevant info on it. I ended up using a bench power supply to provide 5 volts manually and found that the machine drew about 1 amp. The common 7805 linear regulator can do that much easily. However, this little package cannot dissipate the excess heat without a better heatsink, so I made one out of an aluminum plate and some thermal paste. I wasn't sure if it could handle the power dissipation, so I tested it on my bench. Surprisingly, dissipating 7 watts of power only raised its temperature to about 50 Celsius. I went ahead and mounted the new regulators and wired everything back together. Let's see if we've made any progress. Hey! Much better. It looks like the digital logic is at least somewhat working now. This LCD displays some useful diagnostic info about the machine, such as the operating current of various components, as well as the current vacuum levels, though the vacuum level is in percent rather than an actual pressure unit like torr. Weird. Now that the electrical power seems like it's working, it's time to test the vacuum system. I started by testing the pump alone and verifying that it reached about 10 millitorr, which is not fantastic, but sufficient and probably expected for a pump this old. Moving forward, I'm only going to connect the roughing pump and keep the diffusion pump off. This means that our lowest vacuum should be roughly 10 millitorr, assuming we have no significant leaks. I turned the vacuum pump on and used the manual controls to open the valve and evacuate the chamber, but pressure readout on the LCD didn't change. Odd. Perhaps the gauge is broken? Well, sort of. The pressure gauge outputs an analog voltage, which is compared with a set point voltage in order for the machine to operate. All of that worked just fine, thankfully. Quite separately, however, the analog voltage feeds into an analog to digital converter so that it can be displayed on the LCD. That part of the circuit seems to be broken. I tried to fix it but was unsuccessful. Now, fortunately, this won't keep the machine from operating. However, it is pretty important that we know the pressure in the chamber at all times. Running the machine with a leak will lead to an insufficient vacuum, which at best will reduce image quality and filament life, and at worst can lead to a catastrophic failure of the diffusion pump. We really need a vacuum gauge. To that end, I manufactured this aluminum adapter so that I could connect my own vacuum gauge and measure the pressure myself. The gauge will replace the X-ray detector for now. This gauge outputs a voltage between 0 and 10 volts, which can be converted to a pressure reading using this formula. For expediency, I am simply hooking up a voltmeter, and I will overlay the actual pressure in the video where necessary. Okay, So I turned on the rotary pump again, and now I can definitely see the pressure in the chamber dropping. That's a good sign. However, after leaving the system running for several minutes, I saw that the pressure bottomed out at only 200 millitorr. We saw earlier that the pump could do 10 millitorr, so this definitely indicates a leak somewhere in the system. I took a closer look at the connections and yeah, holy cow. These 30-year-old rubber hoses are not looking too good. They have deep cracks almost all the way through. I don't know for sure if they are leaking yet, but even if they somehow are not leaking, if they suddenly fail while the diffusion pump is running and expose the pump to atmosphere, that's not a good day. These definitely have to be replaced. I measured the inner and outer diameter of the hose, and unfortunately, I wasn't able to find an exact replacement. The hose fittings are 24 millimeters, which is not a standard size. To add insult to injury, replacement rubber hoses like this are quite expensive. A few feet of hose would be over $200, which is a bit more than I want to spend since at this point I'm not even sure the microscope will function at all. Fortunately, I was able to find this 7/8 inch, about 22 millimeter, PVC hose reinforced with a steel coil. This keeps it from collapsing under vacuum, but it also might keep the 22 millimeter hose from stretching over the larger 24 millimeter fitting. Only one way to find out. After some persuasion, I was able to make it work just fine. Thank goodness. I replaced all of the rubber hoses and made sure to grease the joints with high vacuum grease, and also used hose clamps to ensure a good seal. I fired the machine back up and darn, still leaking. That's unfortunate. I wonder where the leak is. I spent quite a while inspecting various parts on the machine, using the valves to isolate different segments, and then watching as the pressure slowly climbed. However, nothing seemed like it was actually leaking. I also tried using a stethoscope to hear the leak, but to no avail. I even tried flooding the various connections with 100% isopropanol, which is another method to check for leaks. The isopropanol, if sucked in, will vaporize and cause a spike on the pressure gauge. However, I got nowhere. Every joint on the machine seems vacuum tight. Then I realized my error. If you recall, I tested the pump earlier and verified that it went down to 10 millitorr. However, I didn't check that it stayed that low. You see, when a pump is cold, the oil viscosity is high, and so the thick oil inside can effectively seal tiny gaps. As the pump runs, the oil warms up and becomes more free-flowing, and suddenly, any tiny gaps will start leaking. Now, a new rotary pump would have such tight tolerances that the warm oil would still adequately seal everything. This pump, however, is over 40 years old, and it's likely that it has some serious wear that is causing the leak. Now, if we're lucky, the wear is confined to this part here. This is the rotary shaft seal. It's a hard rubber or plastic bushing with a spring-loaded wiper inside that should seal the shaft perfectly. I pulled it out and replaced it with a new seal. However, I saw no improvement. I decided to disassemble the whole pump and replace all the sealing components. I replaced the external oil seal and the gaskets, but while I was inspecting the inner workings, I noticed two problems. First, the shaft clearly has a huge groove in it from 30 years of wear. Well, that's not great, and isn't really something I can fix easily. I also decided to inspect the vanes, the critical sealing component of a rotary pump. I ended up having to take the whole pump apart just to check them out. Unfortunately, these were badly pitted. I bet you this pump got a little water contamination and then sat for years. I went ahead and put the whole thing back together, but again, I saw no improvement. Now, I would definitely like to make this pump work in the future, but at this point I'd already spent quite a while failing to fix it. And so I decided to just replace the pump with a similar unit. This is a Varian SD90, and it's probably about 20 years old itself, but critically, it's still in good condition and is able to pull a vacuum of about 6 millitorr, which is excellent. I used my lathe to build an adapter from the vacuum pump's KF25 output to a 24mm hose barb to match the rest of the tubing and connected it to my SEM. This time, when I turned everything on, I watched as the pressure dropped well below the 200 millitorr from before, all the way down to about 20 millitorr. Finally, the vacuum leak has been solved and we can move on. Now that we know the system is not leaking, it's finally safe to run the diffusion pump, This pump needs cooling water to circulate through these tubes, or else it will overheat. Fortunately, I was able to scrounge up a small chiller unit that should be just enough to keep this thing cool. I hooked up the tubing and verified that nothing was leaking. After about 20 minutes, the pump was hot and the machine automatically switched modes from DP wait to pre-evac. This is where the SEM uses the rotary pump to evacuate the chamber before it switches to the diffusion pump around about 50 millitorr. Once it reaches that point, it will open the valve and use the diffusion pump to take it all the way down to a high vacuum, about 0.05 millitorr, around 1,000 times better than the rotary pump alone. I waited for the pressure to drop, and yes, the system correctly switched over right around the 50 millitorr mark as expected. But wait. Oh no, we've got a problem. The second valve is stuck and won't open. Well, honestly, what did I expect? These valves probably haven't been serviced in at least 20 years. Looks like it's time for some much needed lubrication. I powered down the SEM and waited until the diffusion pump was back at room temperature. Then I proceeded to tear down the entire vacuum system. The two large valves near the column are responsible for switching between the rotary pump, diffusion pump, and venting the chamber. I slowly and methodically took everything apart and cleaned the valves with acetone and isopropanol to remove all the 30-year-old residual gunk. Then I lubricated all of the moving or sealing surfaces using APazon-L high vacuum grease. Just a side note, you cannot use regular greases or oils in a high vacuum system because they will boil at low pressures and contaminate your system. This is why lubricants designed for vacuum are so expensive. A tube of APazon-L, the size of a travel toothpaste, is a couple $100, and there's really no alternative. Now, if you are in the know, you might be saying, what about Dow Corning high vacuum grease? This stuff is 10 times less expensive, only about $40 for a much larger amount. However, the problem is that this grease contains a bunch of silica, which is abrasive. It's great for static seals in a high vacuum system, but it is unsuitable for any moving parts because the abrasive silica would rapidly cause wear. Fortunately, rather than purchasing the APazon-L myself, I was gifted a couple of CCs by Martin, the other JSM 5200 owner, who happened to have a tube himself. Thanks, Martin. Since the vacuum system is apart already, I'm also going to recondition the RP vent valve. This small valve on the bottom is a protection valve that isolates the entire SEM from the roughing pump. This protects the diffusion pump from atmospheric pressure in case a power outage or other failure causes the rotary pump to stop working. Same as before, I cleaned it with acetone and isopropanol and lubed it with APazon-L grease. After a marathon lubrication session, I managed to reassemble all the valves and get everything reinstalled on the SEM. Boy, was that a lot of effort. Let's see if it paid off. And success! The valve is no longer stuck. Now we can see if the diffusion pump is working. Well, look at that. The pressure is plummeting. I was certain that I'd have to replace the oil in the diffusion pump, but it looks like the pump is operating just fine. After a couple of minutes, it reached a pressure of about 1 to the negative 4 millitorr, which is about 500 times lower than what it was in the pre-evac mode. This is well into the high vacuum region, and is an acceptable pressure for running the machine. Awesome! Now that the vacuum system is working, it's time to see if the machine is functional. Let's turn on the high voltage. Okay, that's a good sign. The CRT is on, which is excellent. This means the high voltage supply is functioning. Let's turn on the electron gun now. This is the knob that controls the current that heats the tungsten filament. You can see that as I turn up the knob, the filament current increases, which is a good sign. That means that the filament is intact. According to the manual, we want to turn this up until the current is between 40 and 50 microamps. We also want to make sure that we don't go too high and blow the filament. I carefully turned up the current until I reached an approximately correct operating point. I feel like I see a difference on the screen, but I don't know. I don't see anything in particular. Let's see if fiddling with the knobs helps at all. Well, the contrast knob doesn't seem to do anything at all, which is a bad sign. The contrast knob controls the voltage on the photomultiplier tube, which is the main electron sensor and what is actually producing the image. Even if the electron gun isn't working at all, cranking up the contrast should at least amplify a bunch of noise and make the screen all grainy. Let's take a look under the hood. Oh wow, that is quite a mess. I looked through the schematics and it's clear that this board here is an aftermarket part. It's actually a board that allows this early 1990s microscope to interact with this box, which can send images to a computer. So basically this board intercepts the video signal and reroutes it through this cable, which goes back to the original board. Wait a minute. Check out this RCA cable. Doesn't that look a bit damaged? I bet you that in the process of modifying this scope, the cable ended up getting into a bad orientation and got kinked when this door hinged closed. Yep, that is one broken cable. Fortunately, I have a replacement. Looks like my cable hoarding comes in handy for once. I'm not sure when was the last time I used one of these to carry an actual video signal. Ooh, that's looking a lot better. Let's see what happens when I fiddle with the knobs this time. Okay, this is a good sign. The contrast is definitely doing something now. This is a good indication that the signal path for the detector is actually working. Brightness seems to work as well. But are we actually imaging anything, or is this just errant electrical signals? The focus buttons don't seem to be doing anything. This might indicate some issue with the circuitry that drives the electron lenses. How about the magnification buttons? These also don't seem to be doing anything. Hang on a sec. Oh wow, the buttons clearly aren't working. I connected my ohm meter to the terminals and pressing the buttons does nothing. Maybe the contacts got corroded. Let's remove them and see if they can be repaired or replaced. Now, normally I would use a soldering iron and solder wick, but this is a pretty high stakes operation and I do not want to risk ruining this board. Fortunately, a friend lent me this fancy desoldering gun, and I've got to say, I really need one of these. This thing made easy work of removing the switches. So now that I've got them out, let's disassemble one of the switches. Okay, this is really interesting. I thought for sure these were mechanical switches, but actually the switch mechanism inside is just a simple membrane switch. I actually thought this microscope predated membrane switches. Well, easy enough. I guess we just need to replace the membranes. I happen to have this old Xbox controller that I don't use anymore, so it's going to become an organ donor for my SEM. Luckily, I only need 4 membranes, and it looks like the membranes on these keys are just about the right size to replace the originals. I just need to carefully cut them out since they are all fused together. Okay, that looks good. Let's reassemble the switch and see if that fixes it. Success! Well, that's awesome. I fixed the other switches in the same way. Okay, time to solder the switches back in. By the way, I did fully power down the unit before doing this, just in case you were worried. Okay, everything is back together. Let's see if I can change the magnification now. Okay, well, the LCD at least says the magnification is changing, but I don't really see any change on the screen. Well, actually, when I zoom all the way out, it does look like something maybe. Wait a minute. That circle might be the center of the specimen stage inside the chamber. Hang on a second. Let's move the stage and see if anything moves on the screen. Okay, I think that might be the stage on the screen. It looks like it moves as I twist the micrometer knobs. Okay, well, that's definitely promising. What if we zoom in a bit? Let's see if we can focus the microscope. Hey, that's more like it. It looks like the image is coming into focus. This is fantastic. I'll be honest, when I first got this machine, I did not expect to get this far. It looks like our repairs have actually succeeded. This machine is actually working and producing images of reasonable quality. I cannot express how happy I am that this machine is working. I know this video has been brief, but in reality, this whole repair process has taken many months, and at several points during the process, I thought all hope was lost. It is extremely satisfying to see this whole project finally coming together like this. Now, obviously, there are still problems that need to be fixed. I noticed that there are some issues with the stability of the video signal, which will probably require identifying and replacing some of the components on the amplifier boards. There are also some issues with some relays. Sometimes when you change the magnification, the image goes all wonky, and then it's fixed when you cycle the relays again. However, now that the machine is operating, I just have to image something. I have this integrated circuit with exposed wiring, and I want to look at the wire bonds that connect the external legs of the IC to the internal silicon chip. This is accomplished with a machine called a wire bonder, which heats and vibrates a tiny gold wire and smushes it against the silicon surface, forming these mushroom-shaped pads. You can see that some of the pads are well formed, while others appear to be misshapen, but are still functional. Another amusing thing about integrated circuits is that occasionally the designers will have a little extra space on the silicon, and some designers will use that tiny space and write messages or graffiti. You can see that this designer wrote, "Go Cards," right here. I'm not exactly sure who the Cards are, but I'm assuming it's a sports team somewhere. I also found this dead fly and put it in the microscope as well. Normally, you need to coat non-conducting specimens in metal for proper imaging, but as it turns out, you can still get a half-decent image if you tweak the settings correctly. In this case, I turned the accelerating voltage down from 25 kilovolts to about 10 kilovolts. Check it out. Here's the fly under the electron microscope. If we zoom in, we can see the individual hexagons of its compound eyes. Pretty cool. Now, you might be wondering, why is the image so grainy? Well, fortunately, that can be fixed. This is a circle of copper that's 3 millimeters in diameter, with a very fine square pattern. Now here it is under the electron microscope. As I adjust the position, it should be obvious that the frame rate is really high. This is nice because it makes it easy to see what you're doing in real time. The downside, though, is that the beam is scanning across the surface incredibly quickly. Because of this, the electron detector only has a very brief moment to capture the data for each pixel. This results in a very grainy image. Fortunately, we can slow down the scan rate. This mode slows the scan rate down to about 1 frame per second. It also displays some useful information on the screen as well. It's a little hard to tell the difference, so let me zoom in a bit. This is a close-up in the fast scan mode. Now watch what happens when I slow down the scan rate. Check out how crisp those edges are now. Most of the high-quality images taken by electron microscopes are done using an extremely slow scan mode, often around 1 minute per image to extract the maximum detail. Speaking of detail, I was curious to determine the maximum resolution of this microscope. To do that, I needed to find something with an extremely small feature size. I found some traces on my chip that were covered in this extremely fine particulate. At 1000 times magnification, the limit of an optical microscope, you can just barely make it out. If we zoom in further, it becomes super obvious that this layer isn't smooth at all, but is instead made up of tiny little particles. Let me enable slow scan and bring up the measurement bar. You can see that these particles are about 1 to 5 micrometers in diameter. Let me find a really small one and zoom in more. Here we are at 100,000 times magnification. This particle is about 200 or 300 nanometers wide. Those wavy edges are actually caused by vibrations, which is something I'll need to reduce if I want to improve the resolution further. By the way, remember the computer that I showed earlier? I did actually manage to get it working. Well, sort of. It comes with software that allows you to capture images directly off of the microscope. Here are those grains from earlier. Now, this thing definitely needs some work. It's got some pretty serious signal integrity issues, but I did manage to capture a few good still images. Here are those small particles again. This is the highest resolution image I was able to get. So where do we go from here? Well, obviously, there is still more work to be done. There are some components on the machine that still aren't working optimally and need to be replaced. However, the most pressing thing for me is to find out what I can actually do with this machine. This is probably going to be the subject of the next video, and to do that, I need to accurately determine its resolution. After that, I should be able to start using the machine to help me develop semiconductors in future videos. Now, I just want to make it completely clear. It is not necessary to have a scanning electron microscope to make semiconductors at home. An optical microscope is usually more than enough. However, now that I have it, I will definitely be leveraging this SEM for future semiconductor development. In addition, I'd like to get input from you, the viewers of the channel, on what I should do with this SEM. Would you like to see more detailed videos of how electron microscopes work? Do you want to send me things to look at? Feel free to let me know in the comments if you have any ideas. In the meantime, I want to thank you for watching. I honestly didn't know if I would ever be able to make this video, and I really appreciate everyone who stuck around. I also want to thank my patrons on Patreon, as well as the members of the SEM Discord channel for all of their encouragement and advice, especially Martin, Did Shadow, and Monochroma. I couldn't have done this without all of your help. Thank you, and I'll see you next time.